This is our final project for Data Science Lab doing object detection using YOLO. So to start, object detection is a critical task in the field of computer vision, aiming to identify and locate objects within an image or video. It goes beyond classification by recognizing what objects are present in the scene and pinpointing their exact locations. With the recent rise in self-driving cars, the use of computer vision to detect major road obstacles has become increasingly prevalent. This application can be integral for many different applications, from advanced driver assistance systems to autonomous vehicles. In order to properly tackle this problem, we used data from Cityscape's dataset. We analyzed all the cities under the validation and training sets, and due to the robustness of the dataset, we believed it to be most efficient to leverage a pre-trained model or framework. So the framework we chose was the You Only Look Once, or YOLO model, which predicts bounding boxes and class probabilities from images. YOLO is known for its speed and accuracy, making it especially useful in real-time object detection. Given the already annotated images from Cityscapes of images of signs, pedestrians, and vehicles, YOLO uses the training set to learn the features that correspond to each object class. We used 7 labels for training, meaning the model was learning to associate 7 different labels based on visual features. For evaluation, we also used all 7 labels to measure its ability to accurately detect each object. As our motivation, in the past decade, as public and corporate interest in autonomous vehicles has surged, a paramount concern has emerged: safety. Central to ensuring the safety of these self-driving vehicles is the efficacy of their computer vision systems. These systems must accurately and efficiently detect and identify diverse forms of traffic and obstacles encountered on roadways. Given the complexity of real-world driving conditions, ranging from pedestrian-filled urban streets to dynamic highway scenarios, the capability of autonomous vehicles to perceive and react to their surroundings remains a critical focus of research and development efforts. The ability to reliably interpret and respond to a myriad of visual cues, from traffic signals to unexpected hazards, stands as a pivotal challenge within the realm of data science, demanding innovative solutions to ensure accurate and swift detection of diverse traffic conditions and impediments.
One of the key challenges in building autonomous vehicles is the ability to accurately detect and classify objects in the environment like pedestrians, cars, and cyclists. To address this, machine learning techniques like object detection and semantic segmentation have been employed. Our team used the Cityscapes dataset to train on it. This dataset contains dense semantic segmentation and instance segmentation for vehicles and pedestrians, providing a diverse range of scenarios for analysis. This dataset spans 30 classes across 50 cities and various weather conditions, and it comprises 5,000 images with fine annotations and 20,000 with coarse annotations. For our purposes, we're using the fine dataset and left train val test dataset. The train val test dataset contains fine annotations for training, validation, and testing sets, while the left train val dataset contains the corresponding left camera images. These images are captured at a resolution of 2048 by 1024 pixels, providing a high level of detail for object detection. The Cityscapes dataset is a great foundation for object detection due to its user-friendly formatting and surplus of training and testing data. Research on these datasets commonly deals with vision-related tasks such as instant segmentation, object detection, scene parsing, and semantic segmentation. The use cases are far and wide, with the most recent advances in autonomous driving and augmented reality. All of these categories present an intuitive manner to train and test the models. For our purposes, much of the work was done using the validation data to test our YOLO model. The goal of this research is to leverage features of YOLO V8 for accurate and efficient object detection. On the Cityscapes dataset, we aim to achieve high precision and recall rates for detecting various classes of objects, including pedestrians, vehicles, road signs, in a complex urban street setting. To assess the performance of our models, we will be using 2 standard evaluation metrics: mean average precision and intersection over union. Mean average precision, or MAP, is a widely used metric in information retrieval and object detection tasks to evaluate the performance of a model. It measures the accuracy of the model in retrieving relevant items or detecting objects from a pool of items. In the context of object detection, MAP is calculated by computing average precision, or AP, for each class or category of objects detected by the model. AP measures the area under the precision recall curve for a specific class. Precision is the ratio of true positive detections to the total number of positive detections, while recall is the ratio of true positive detections to the total number of ground truth positives. After calculating the AP for each class, the MAP is obtained by taking the mean of this. This provides a single scalar value that represents the overall performance of the model across classes. MAP is particularly useful in scenarios where there are multiple classes or categories to be detected, as it provides a comprehensive evaluation of the model's performance across all classes rather than focusing on a single class. The intersection over union is a common metric used in computer vision tasks. It measures the overlap between two bounding boxes and is defined as the ratio of the area of intersection to the area of the union. In this context of object detection, IOU is used to evaluate the accuracy of bounding box predictions, where the area of intersection is the region where the two bounding boxes overlap, and the area of union is the total area covered by both bounding boxes. IOU is used as a threshold for determining whether a predicted bounding box is considered a true positive or a false positive. We used a threshold of 0.5. If the IOU score is above 0.5, the prediction is considered a true positive instance.
Yeah, so YOLO, or You Only Look Once, is a real-time object detection system that is widely used for computer vision applications. So we used YOLO v8, which is the latest version of the YOLO object detection algorithm. And this version just builds on the previous versions with several improvements. So one of the main improvements of YOLO v8 is the use of a new backbone architecture called CSP DarkNet, which is based on the DarkNet convolutional neural network. And so it improves the accuracy and speed of YOLO v8 by reducing the computational complexity of the network. YOLO v8 also includes several new features, such as support for multi-scale training, which allows the network to learn to detect objects at different scales, and support for mosaic data augmentation. For this task, we used an open-sourced implementation, Ultralytics YOLO v8. So Ultralytics YOLO v8 provides a Python API for training and deploying YOLO v8 models. It supports a wide range of features, including multi-GPU training, transfer learning, and real-time inference. It also provides pre-trained models for various object detection tasks, such as person detection, vehicle detection, and face detection. Ultralytics YOLO v8 has a really good performance, right? So it's optimized for speed and accuracy, as you can tell in these two graphs that we have on the slide, and it can process images and videos in real time.
All right, so for our implementation, we first dealt with the pre-processing. Here we converted irregular polygons enveloping objects to a standardized rectangular shape. The Cityscapes dataset provides precise pixel-level annotations for the objects that are represented as irregular polygons. However, our YOLO model requires bounding box annotations, which are rectangular in shape. To address this issue, we used an open-source script to convert the Cityscapes annotations to the COCO format. The Common Objects in Context, COCO, format is widely used dataset format for object detection tasks. This code calculates the minimum and maximum x and y coordinates of each polygon to create a tightly fitting bounding box. The resulting bounding boxes were then converted into the COCO format, a widely used dataset format in object detection tasks. The next step is conversion. Here we used a object detection pipeline to convert the COCO objects into YOLO format. This step is crucial for training our model effectively and facilitating our scoring mechanism. The YOLO format represents each bounding box by its center coordinates x, y, width w, and height h, normalized by the image dimensions. This format also represents each object class as an integer, which is more efficient for computation as compared to the string representations used in COCO. The first step that we did, convert the bounding box to bounding box coordinates. This involves calculating the center coordinates, heights, width of each bounding box, and normalizing these values by the image dimensions. We then map the COCO object categories to integers for the YOLO format. The initial process involves a conversion of bounding box coordinates, which is managed by Ultralytics JSON to YOLO script. This script is adjusted to improve its compatibility with the output of the Cityscapes to COCO conversion, since it didn't support nested directories in its default configuration. This new conversion will also support our scoring mechanism, which is based on the intersection over union metric. The YOLO format's representation of bounding boxes make it easier to calculate the IOU between the ground truth and predicted bounding boxes. Lastly, for our training, we used YOLO V8, which is a state-of-the-art object detection model, which we use to retrain with our data and with the aim of creating a custom model capable of detecting cityscapes labels accurately. The training process involved feeding our YOLO formatted data into the YOLO V8 model. The model was initialized with pre-trained weights, which were fine-tuned to our data. This approach, known as transfer learning, leverages the model's prior knowledge of feature extraction, thereby improving its performance on our specific task. The YOLO V8 model uses a convolution neural network to extract features from the input images. These features are then fed into the detection head, which predict the bounding box coordinates and object classes for each detection. The model is trained using a loss function that penalizes errors in both bounding box coordinates and object classes.
All right, so now let's talk about the results. So first off, we trained YOLO V8 for 60 epochs to try and improve the model's compatibility with the transformed dataset. If we look at just the map 50 values with no training, we get roughly a score of 0.01. However, after 60 epochs, we can clearly see that that has improved because we were getting 0.5 and higher. However, we also saw that the model began overfitting after roughly 30 epochs, but transfer learning was still partially successful for certain classes like the airplane, motorcycle, train, and bicycle. Now, taking a look at the confusion matrix for both the no training and the 60 epochs training, we can quickly take a look at the amount of each predicted class that we got wrong and in what category. If we take a look, we can see that the car-to-car box in both models has a deep blue color, showing us that there are many cases where we predicted car and our ground truth was also car, which is very good. However, we can also see that there is a lot of blue in the bottom area. This is when we predict background and the ground truth was not background. This is because YOLO seems to not work very well with objects far in the distance of the image. This leads to many of those objects being incorrectly identified as part of the background when in reality they're other objects. Additionally, even though the hues on both of our confusion matrices seem very similar, the untrained model has a dark blue hue of 0.8, whereas the trained model has a dark hue at 0.6. This means that even though they look similar, our trained model has a much lower chance of getting things wrong than our untrained model, which is exactly what we are looking for.
So here we can see the precision recall curves of both the 60 epoch train model on the right and the YOLO model without any training on the left. Looking at the performance for various labels, we can see that the precision recall is much more balanced and has a much higher area under curve for classes such as motorcycles, bicycles, and people. This is likely because of the fact that the base COCO dataset does not have as many instances in context as the Cityscapes dataset does. This much more balanced precision recall curve indicates that our model, after retraining, is much more performant and capable of detecting objects that we were looking for. Now we're going to look at some examples of our object detection model in practice. So the original image is shown on top, and the base YOLO image on the left, and the retrained YOLO image on the right. Looking at the base YOLO image, we can see that it incorrectly identifies a window in a building as being a truck. And if you look at the retrained model on the right side, we can see that it's no longer detecting that as a false positive. Furthermore, you can see that a person in the left side of the image is also now detected, whereas it wasn't before. Another characteristic of our model that we can see is that it's really easily able to detect cars. There's really high confidence, and it seems to detect pretty much every car in the image there.
Taking a look at a second example, we can see that in the base image, we're incorrectly classifying a bus as a train. After retraining though, we can clearly see that YOLO does classify it as a train with 0.92 probability. However, we also can see that the retrained YOLO failed to recognize the traffic lights and thought that the truck was in fact a car. This is probably due to the fact that our dataset has many more car class instances than any other type of vehicle. So the relative responsiveness of non-car classes is decreased compared to the base model. In conclusion, we retrained YOLO V8 on the transformed cityscapes dataset for 60 epochs to improve its compatibility with the dataset. The map 50 results for all of our classes improved after retraining, indicating that transfer learning from our base YOLO model was successful. The PR curves also showed improvement for certain classes like airplane, motorcycle, train, and bicycle, indicating that we have a much more responsive model. However, we also found that YOLO struggled with objects far in the distance of the image, leading to many incorrect identifications as background. Despite this, the confusion matrices showed a decrease in false positive and false negative rates for all tested classes after retraining. The results also showed that the model's performance improved in detecting certain objects, such as people and trains, but struggled with others, such as traffic lights and trucks. Overall, the results suggest that transfer learning was partially successful, but there is still plenty of room for improvement in detecting certain objects and dealing with objects in the distance.